All right. So welcome everybody to the main act of this conference. This is the main act because it's the SQL talk. You all came here to hear about SQL and this Java thing. This is the stuff we have to do, but if you really want to listen to our hearts, we're going to write it in SQL. How modern SQL databases come up with algorithms that you would have never dreamed of. And I'm really happy to be in the big data machine learning track here because, I mean, what is big data? It's just classic SQL, right? Now, I've seen a lot of Java developers try SQL, and every time I see them, I kind of sometimes have the feeling like this. I see them like this, trying SQL. What is this SQL thing? How does it work? It's a miracle, right? I always say SQL is a device whose mystery is only exceeded by its power. This is me, Lukas. I'm the founder and CEO at Datagate, a company from St. Gallen, Switzerland. I'm mostly involved with Oracle, but also doing other SQL-related things. I talk about SQL because I love it. It's the only ever successful mainstream and general purpose fourth generation programming language. I keep saying that in every talk because it's something so important to remember. A fourth generation programming language that was the dream of everybody in the 60s, 70s, and now finally with modern optimizers we can have the promise that we had already in the times. We don't write the algorithms ourselves because the machine figures it out for us. We just declare everything. This is also why the company is called Oracle. You ask it a question, it gives you a very expensive answer, and you have no idea how it got to the answer. Why doesn't anyone else talk about SQL? Well, that's not true. Chris is here. He talked about JSON in SQL databases in the morning. But usually at Java conferences, I'm always the only guy talking about SQL. I have absolutely no clue. After this talk, you will agree with me because everyone should be talking about SQL. Actually, who has seen my other talk? I think I had my other talk here as well in Ticino. I mean this one, I mean this talk, right? Who has seen this talk? So this was a talk about SQL being awesome, right? If you have missed it, it's not hard to find. I can also give you some advice on search engine optimization. If you type 10 SQL tricks, you will find me 10 times on #1 page of Google. I'm really good at this as well. But now, a SQL trick from that other talk would be this one. So in the front row, you can already read it, and then you have deciphered it. It's Postgres, as you have undoubtedly immediately recognized, and you have processed this in your head, and that's the result. Exactly. So SQL is a Turing-complete language. It has recursion. This means you can do nice things like the Mandelbrot set in SQL. And it's actually not that difficult. The bottom part is just string formatting, and the top part is a very simple function recursively, and you have the Mandelbrot set. So your application is actually sitting on a Ferrari-style computation engine, especially if you purchase the commercial databases, it's a Ferrari. If you purchase, or actually you get it for free, MySQL maybe it's more a Fiat Punto, but it's really a computation engine that you can really do miraculous things with it. It's not just what a lot of Java developers think. It's not just a storage engine, right? So you get ACID, and that's nice. Now, some competitors think that's not so important. You have NoSQL databases where you don't have ACID, so it's eventually consistent. You're lucky even to have your data where it belongs. With SQL, you get ACID, but you also have a computation engine, which is really miraculous. I will talk about this today, what that really means. Now, I'm in the big data track. I should also be in the microservice track because SQL is the original microservice. You just install one store procedure in an Oracle Express Edition instance and deploy that, and you're done. That's a microservice. We did that already 20 years ago. Now it has a new name. SQL is also the original blockchain, right? I updated my slides. I go with the time. So SQL is the original blockchain. This is actually not my idea. It's by Michael Simons from Germany. He should follow him on Twitter. Very funky idea. You can actually create a hash and then recursively hash that hash again until you get the blockchain, right? So SQL could do that 20 years ago already. Now it's called blockchain, and it makes you a lot of money if you are into venture capital. Now I'm in the machine learning track, so SQL is also the original machine learning language. Why? Because we've had linear regression functions since decades. We all knew this stuff. Now we just use it, right? When you're doing these things, just use SQL. But today, we'll talk about more basic SQL. So my other talk was about that 10 SQL tricks talk. It was really advanced, on top of everyone's head, sometimes even my own. When I read the slides again, I kind of have to think, what am I going to talk about now? But this one is still awesome, even if it's basic SQL. So just to get everyone on the same level in this room, everyone in this room recognizes this to be SQL? SQL? Everyone? Yes, you recognize? Perfect. So this talk is for you. Excellent. Now in the other talk, I already discussed in the other talk why SQL is awesome, so we don't have to repeat that again. You already agree it's awesome. Now I want to focus on these other two bullets. SQL is productive. That means you are productive when you write SQL. And SQL is also fast. So this is the two parts of my today's talk. First, let's focus on SQL making you productive as programmers. Now, there are two ways of proving this, right? So by example, this would be very academic. I would show you examples, proofs, right? Mathematical stuff. It would be on top of everyone's head, boring. Or by alternative, I like this kind of style, right? A little bit of bashing. You all came here for this. So this is going to be a high-level conceptual story about SQL, and we're not going to deeper levels, right? So business is asking us a question. We have this wonderful schema. I like it for all my trainings and presentations. It's a Sakila schema. We are a DVD rental store. So obviously we rent films, and films have actors, and films have categories. It's very nicely normalized, so many-to-many relationships. And now we have several films. Each film we have several times in the inventory, and then we go over to the rental table where someone can rent a film from the inventory, and they can even do partial payments with this wonderful schema. And there are customers, of course, etc. So you get the point. Everyone has a schema like this in production. Now what happens when we have these schemas? We're just sitting there, minding our own business, playing with Nerf guns, and then business comes and gets on our nerves with questions like these. How much money did we earn with each film on each day, right? So that's a business question, serious question. We have to figure out if we're profitable. And you're sitting there thinking, all right, okay, I can do this. Let's check. This is my schema. So this is the films. We need to know how much money per film and day. So the money's over there. Okay, great. Oh, and the day's over there as well, because the payment has a payment time, and that's the day when we made any money. So we have to somehow find this path here. That's probably what we want, and then what we do is, exactly, we join. Wonderful, already the solution, easy, right? So we do this join. We're going from the money per film. We want to first collect the film table, then we somehow express the relationship between the film and the money, and then we aggregate per film and date, and we're done, okay? So everyone can go to the next talk, so easy. Now, I promised you I want to do this with Java as well. Now we're going to do this not just with Java, we're going to do this with enterprise Java, and we're going to feel good about ourselves because that's where we are at home. We want to write Java. So let's first start with the film class. Obviously, just like creating a table, we have to create a class. So you're still with me, right? That's okay? Good. Now, obviously, a film is a tuple or tuple. I don't know which one is more hipster these days. What is a tuple or tuple? Now anyway, a tuple or tuple has attributes. So that's the same thing as in the database when we create a table with columns, or in the relationship model, the relational model, we call it an entity with attributes. Here we call it a class with members. It's always the same thing, right? So we have something that we give a name, and then we have attributes. This would be what we would expect from Java, but it's Java, so we can't just stick there. We have to do these people as well, right? So these folks have to be in there as well in the class, because maybe at some point in the future we want to switch the implementation, right? Maybe the film ID is going to change somehow in the future, so we must not give direct access to this film ID attribute. This feels we feel safe, now we feel better about ourselves, but we're not done yet, right? We have to implement these folks as well. Right? Everyone enjoying themselves, hash code. Okay, we're generating these with the IDs, or maybe we have some fancy library, but we will have to do this because otherwise it's not complete. Anyone ever did this kind of stuff with SQL? No. Okay, but we're not done. We're not done. We've learned design patterns, right? All of the design patterns. Gang of 4 design patterns. We must absolutely not allow any junior developer to instantiate these things recklessly. We must instantiate through a film factory. Yes? The constructor must be hidden. We don't know the life cycle of the film entity yet. Better play safe, right? And the same thing happens with the film factory. Who can instantiate the film factory? Only one type can do that. That's the film factory builder, right? Okay, so we do a new film factory, new film, and then it's still wrong because it's not polymorphic enough. Of course, we can have classes, but classes can only have one subtype, and we want to do mix-ins and whatever we need later on, so we have to create interfaces and implementations. Okay? We're all set? Okay. Now, who's using Spring? Everyone. So you will add these folks as well. Put some annotations, probably because you want to manage the life cycles and have singletons that are managed and you can redeploy and mock, etc. And you all thought about, okay, I'm not going to write getters and setter myself. I use this tool called Lombok. We're going to add some annotations here to our enterprise Java Bean and some more annotations. I see some interesting things here in the Film Factory Builder implementation. Oh, what the heck, we'll add these as well. And I recently called my friends in the ISS. They were just flying over Switzerland. Hey folks, can you please send a picture? I have something here. Can you see this? And they saw my enterprise Java Beans from space sitting right there, right? Okay. So if you want to learn more about the annotation stuff, I'm not going to focus on that, but here's a nice page to get involved with annotations. But we're not done. This is just a film entity. So now how do we get from the film to the inventory to the store to the rental to the payment? We have to do these joins as well. It's the same thing, Java or SQL, we have to do some sort of join. What do? We add another getter, so we add a getter that gets us the inventories. More or less one-to-one mapping to the relational model. Now everyone is using these, right? Excellent. So this one helps us not worry about whatever happens behind the scenes. We just want to get to the inventory, etc. So you have all seen these things. Now, who in here knows which one is better? Yes? Want to discuss this? Again? All right. Perfect. Now let's assume we get it right, which we never do. The next question is, finally we found the path from the film to the rental. Now this is the result we want to get, right? We want to have the film the money per date per film. I actually have an animation here. So this is the money because we're not going to use double, right? We've learned that. We're using big decimal, no rounding errors in money calculations, per film and per date. Okay? Now, I'm keeping it simple here. Obviously, you should add an abstraction. We can't just use a big decimal for money. That's just a numeric type. It has no meaning at all. We need a money API, and there's luckily a JSR for this. There's a Java Money API, and it fits our purpose perfectly, right? If you look closely, it is designed exactly like we want it to be designed, so we can override and mock its behavior. We have the monetary amount factory provider SPI query inclusion policy. Okay? So I don't make this up. This is actually true. Now, let's keep it simple. Keep it big decimal. You can imagine we have a money type right there and the real world application, but it should be this or this. Yes? What's better? Do we want to maintain the insertion order so we can reproduce easily how we ordered the query in the UI or in the for loop or not? It's going to make a difference. Or maybe this. So we don't actually have to think about it. So we can sort by the film because that's what we want in the UI, right? And we have these comparators that we can put in tree map. Or maybe, I know, everyone has a junior in the team, and when they first understand all the contracts, hash code equals, etc., what are juniors going to do? They're going to write a library, the multi-key map, because it sucks so much to nest a map in a map, so we need a new map that has 2 keys. Right? We have a map that has film and local date keys and big decimal value. And while we're deciding for the correct collection type, you're all sitting here, when's the talk going to end? So, who in here has felt this way before? Yes, all yes. Okay, now let's calculate. I'm just explaining how I want to have the result. Let's calculate this thing. We want to have a map of film, and for each film, per date, the money we've earned. So we're going to load all these films, and then there's this eager and lazy thing. So we have some problem here. We're going to fix it later, right? There's a comment from 2002. Yeah, seriously, we're going to fix this, but no one knows how to do it. We're going to do this later. Now for each film, we have to iterate. We love iterating, right? So we go for each film, and then we get this map out of the result map. We've initialized that in the beginning. Let's ignore which map it was. And we get, for the film, the map of date and big decimal, right? So this is the same type. We recognize this. But it's difficult, right? Because it's Java, this is going to be null, and we have to lazy initialize it. Are you enjoying yourself? Lazy initialize. Every time you have to think about this. Yeah, you have to think about this every time. And, what is here? Oh, the nested map. Should that be a hash map or a linked map? Yes, right. Okay, we've solved this as well. I've put it in ellipsis here, so we're ignoring it for now. We're going on to the next problem. For For each film, we need to get the inventories and then the rentals and the payment, just like in SQL, right? And now we remember, is it eager or lazy? And what happens if it's lazy? But you read in a blog post that eager is a code smell. So which is your best choice here? Wow. Okay, if you run this lazily, and I have 1,000 films in this example database, and maybe 50,000 payments, how many queries will we get? About 1 billion. I tried this on my work computer at home, and it's still running after 5 years. Okay. But we could use the entity graph. We could use the entity graph. Luckily, JPA solved this for us. This is how JPA solves queries. They have about 5 of these different types of querying systems. Also, the criteria API looks also very nice. Anyone want to do this? Entity graph? Who uses entity graphs? Yes? You feel lucky? I don't. Because by now, I've added these annotations before it was like this, and now I really, the ISS didn't see the class anymore, it was so big, so I had to call a little bit further away. I called my friends from Andromeda Galaxy, can they take a picture? And they saw it right there. This is where my enterprise Java Bean can be seen from the Andromeda Galaxy. But we're not done, so we're looping, and we're in the middle of this loop, and now in the middle of this loop, we have to put the amount and the date in the map. In the nested map, right? Is this correct? No, it's wrong. It's wrong because once more we have to lazy initialize the value. It was null, right? Because the first time we encounter the date, we have to actually initialize it in that area. And if we already had the date, then we can add it, right? So at least in Java 8, this got a little bit better. You see, I can save 2 lines here. Got much better. I have these compute methods where I can do this a little bit more concisely. So it's a little bit better now. But you feel good about yourself? Great. Excellent. So we've done this. We've solved our assignment. Business is happy. But what happens every single time? Business long forgotten that they had this request. They come back. Oh, yeah, you're right. I'm sorry. Did I say how much money per film? I meant, of course, per film and store. Yeah, when does that ever happen, right? Changing requirements. So how do we react as programmers? There are 2 types of reactions. The SQL developer reaction and the Java developer reaction. So this is a footage of a SQL developer. I got you covered. I know how to do this. And here's a coverage of the Java developer. Yes? Yes. We can all relate to that. Yes. Do it. You knew you wanted to do it. Out of the window. So the SQL developer, I have here some exciting PowerPoint skills that I want to display to you, is going to do this. Yes? Save some space for what they're going to add next, and then, done. Yes? How much money do we make per film and store and date? Done. New report, perfect. The Java developer does the same thing. Oh my God, look at the space that we're reserving. It looks better and better. All right. And then there's the architect. Now this happens as well. Every time we commit, this architect person shows up, and that's this guy, in case you've ever worked with an architect. He sees every one of your commits, and he says, we cannot have such types. We cannot have maps of maps of maps. We need to factor this out in a new class, and the class has to be named for this use case, and then we need a factory. And while you're thinking, oh my God, I'm going to debate this, I don't know, you're going to discuss maybe structural nominal typing philosophies. Yeah, you know, I've read in a functional programming blog, we can more structurally program. We don't actually need to name everything, but it's Java, you have to. Meanwhile, what happens? You're interrupted again. So he's coming back. Oh, did I say daily revenue? I meant cumulative daily revenue. Oh my God, I'm sorry, I'm not focused today. What does that mean, cumulative daily revenue? So you go to the internet, and you start typing. Cumulative sum, and you hit enter, and bam, you see this, and then, oh, it's Friday. I'm not going to do this anymore. I'm not going to. Meanwhile, the SQL developer will reserve, admittedly, it's a bit more than just another group by. We have to add this thing here. Okay, that looks a little bit scary if you've never seen it, but it's actually very simple. Just with this, we can have, it's called a window function, we can have the cumulative daily revenue. So this is the result. We had per film and store and date. We had the revenue of that date. So this is the sum column, and the cumulative sum will give us the cumulative sum from the beginning of time until today. So it's like Microsoft Excel spreadsheet. You run through the spreadsheet. It's a running total, right? So this is wonderful. You can do these kind of things in SQL very, very easily. Now, you have to learn it, of course, but learning is exciting, right? So we learn this, and then we don't have to worry anything anymore about algorithms. You get the message, right? So the first message I'm trying to say here is, yes, I can explain this. I have a training, so I can tell you how window functions work. So that's one way. And the other thing is, SQL is a 4GL, a programming language of the first generation. I have declared this running total, and I don't care about the single hash map, linked map, whatever. I only declare the result. The database will figure out the algorithm for us. Algorithms are boring. Now, they're very interesting, don't get me wrong. I love algorithms, but we don't want to think about algorithms every single time we write business logic. Now, if you write infrastructure logic, which is what I call it, like a library, and you offer that to everyone else in the company, obviously that's something entirely different. In that case, please do get the algorithms right and the data structures. But if you write business logic, we need to be able to react quickly to what business says now. And with SQL, that's much easier than with any imperative language like Java or all the others. So we don't care about things like writing algorithms. Again, using them is a different story. Now, even if you use SQL, you need to know algorithms to understand what the database is doing when it's using an O of n or an O of log n algorithm behind the scenes. But we don't want to write them all the time. We don't want to optimize all these things all the time. Most optimizations are premature. Should we optimize this for loop? We haven't even discussed the data set size. Are we going to query 10 rows or 100 million? So optimization is really hard. If we write the algorithm ourselves, it's even harder. We don't care about data type details most of the time. We care about business logic. So if it's a hash map or a list of entry, which is kind of the same thing, more or less, if you squint a little bit, but do we care about this all the time? Probably not. So we just default to hash map all the time, but sometimes it's not the best type. Local variables. Now, who has enjoyed writing a local variable, storing it, and modifying it? It's all mutability, etc. We don't enjoy that kind of things. We don't enjoy caching, but we would have to cache stuff all the time. We don't enjoy writing loops. It's boring. And we don't enjoy initialization. And I don't even want to start a discussion about optional, right? So we can have this null or optional. It's the same thing ultimately because we have to think about it. Now, optional helps us a little bit with the type system, but it's still very low level. What we do care about is business logic, and then a little bit of indexing usually helps us just enough to get it right. Now, of course, you have to tune the database as well, know your stuff around the database, but understand it like this. A database query goes wrong 1 in 1,000 times, maybe, or maybe twice. But our Java code can go wrong at every single loop. So we don't care about that at the same level anymore. Now, I'm very happy I give this talk. Now I have Mario Fusco personally here. I have a quote here. The Stream API changed everything, right? So we have this really nice representation. I really like this tweet. It's very concise and shows the advantage of the Stream API. So this is kind of like the from clause, and this is kind of like the where clause when we have a filter. And this is kind of like fetch next or limit in SQL, right? We have that as well in SQL, and then collect is kind of like group by and an aggregation. So SQL and streams are kind of similar. When you work with streams, you let go of that imperative thing where you have to instruct the machine to do everything like that. It's more declarative. It feels declarative. It's a lie behind the scenes because you're still saying the exact order of operations, at least in the current implementation. This might be able to optimize in the future, but as long as we have the option of bringing mutability inside of the stream functions, the streams can't really optimize a lot. But if you think about it in a programming model way, it's really nice because a stream of tuples is like a table, right? So a Java class is a tuple, and it's kind of like a table. So you have the stream of records. And map in the Stream API is just like select in SQL. Select is a function. No, select takes a function as an argument, which takes an input tuple. I have to make up my mind, so I'm going to say tuple now. The input tuple and produces an output tuple. It's a very straightforward function, right? So map is the same thing. It gets an input object and puts out an output object. That's kind of like select, and distinct is obviously the same thing. Join and flap map are almost the same thing. You can think of it this way. We have two streams that we join together with a flap map function, kind of the same thing. Where and having is like filter, so in SQL we have two keywords for one thing. Group by and collect are the same thing, order by, sorted, uninull, and concat. So we can rewrite this algorithm. And I'm going to speed this up a little bit. Usually if I have 1 hour, I'm going to walk you through the entire refactoring of this mess to the next mess, because we want to do this in the end, right? Load all the films, then stream them, then flat map them to the inventories, and flat map them to the rentals, and flat map them to the payments. But there's one problem with flat map itself, because we're losing all the interesting types. When we use flat map, we get a new type, right? So now at the end, when we can collect the payments, but we've lost information about the film. We want to group by film and date and amount. So from the collector, we can't easily access F and I. We can, of course, instead of just flat mapping, streaming that as well and mapping it and wrapping it with this entry. So I'm using like a map entry here. And then hope and pray for stack allocation to happen. So this was the talk by Chris Talinger this morning. Maybe with Graal this works a little bit better, but we have many objects that we have to allocate just to wrap these things. And then this nice group by operation here. Okay, what is that? It certainly looks declarative, right? It looks declarative. A little bit of advertising. There's Julanda, a stream API, better streams if you don't need parallelism. So that was a design choice by the JDK teams. They wanted to have parallel streams and a lot of nice features on streams that could have been done on a sequential only stream had to be omitted because it's much more complicated with a parallel stream, like zip with index. We're all missing that. But with a parallel stream, zip with index is kind of complicated. So Julanda adds a couple of features. It actually implements a stream, but it's a little bit more. So we can, for instance, collect several aggregate functions in one go, just like in SQL. This is kind of missing with classic streams, so we have a tuple in the end that's coming out of this aggregation. And now we can refactor this step by step. So instead of stream, I use this sequence, which is just a sequential stream. Instead of flat map, I can use cross-supply, which is Oracle and SQL Server. So it's inspired by the SQL language, some keywords. So you can now cross-apply. This remembers the old type, also wraps it for you. Still the same overhead, but at least you can get these types. So if you're lucky, generics will work for you. And then you can now group by here, and you have all the information available. But we actually never needed the rental, so we can skip this. It gets a little bit better. I'm just skipping through this. In the end, also the result type is a little bit better. But how much time did I spend on this topic? And only if we were lucky, the compiler will actually compile this. Who has ever sent a type witness to these kind of stream operations? This is hard. Type inference is hard. And all these types, sometimes you're just losing out on something. And you're all, okay, what's the point? Yeah, I got it now, right? So this was the SQL solution. That wasn't hard. I spent about 30 seconds on this. SQL is a fourth-generation programming language. This means you are much more productive. You don't want to have these discussions, even with streams, which are better for ordinary use cases and more concise. If you want to stick with this model, and if your data set is not really inside of a database, you're transforming some whatever that is in the client. But my message here is that translates pretty much on the time you can spend. SQL is easier means SQL is more productive for you, for data set processing problems. So this has been proven, or at least shown. Proof is something else. Now this interesting thing is, how is the database interpreting that? And why is it also interesting and better for the database? That's the performance chapter. Much more important. So how does SQL work? Let's look at another business case. So how many films did each actor whose last name starts with A play in? Another interesting query. So this will be the result. So these actors start with the letter A, and that's how many films they played in. Right? So that's maybe the business case. We want to find this out. And this would be the SQL query, more or less. I forgot one group by column. There should be actor ID as well. Now we group by first and last name, filter all the actors whose last name starts with the letter A, do the join, etc. So there are three things to consider. First off, this is the syntactic order of operations. And that's what everyone criticizes about SQL, is the syntax. Because it's originally SQL, structured English query language, the first word is the command we want to execute. So it's English, so we command the database, it better now select something, right? So that's the select verb that's first, even if logically, if we redesigned the language in a better way, in a better syntax, logically we would first do the from clause. Like in the stream API, the first thing you do is you initialize the stream data set and then you reduce it, right? So that's logically. That's still not what actually happens. I will get to that afterwards, but that's what we should understand logically. So now if you're not using SQL every day, and you have to analyze some SQL statement that your coworker wrote, and it's really funky, and you don't understand group by very well, maybe think about the logical order of operations, because that's how you should read SQL and think about SQL. So from and join is the first thing. Actually, join is just an operator. Join is not a keyword. Join is a relational algebra operator, just like plus and minus. And then the second operation is the where clause, where we filter the last name. Again, this is not what is happening first in the actual operations, but logically. The third operation is the grouping. And while we group, we can aggregate. And if they're the same aggregate symbol, like count star, count asterisk, that doesn't mean it is calculated twice. Depending on the database, it might be, like Postgres gets this wrong, apparently, still. But usually databases will realize, so this is the same value. They can analyze SQL. SQL has no side effects, in theory at least. Sometimes it has, but in theory it has no side effects. So the database can easily prove that this must be the same value, so we don't calculate it twice. We substitute the function by the value, like in functional programming, right? So in functional programming without side effects, when you memoize a function, you can always replace the function expression by the value expression. So then, after we've calculated count value, we can project. So that's the select clause. We call it projection. Also, JPA calls it a projection if you don't select an entity. So we project the first name, last name, and this count value, and then we order by the count value. That's the logical operations order of this statement. The complete operations order is here, almost complete. So from is the first, where next. So there's some Oracle-specific ones, which I don't want to talk about, but group by and aggregations happen next. And then, because aggregations are here, they're here. This means you can only use them afterwards in this order. You cannot use a count expression in the where clause, because that has already happened, logically. It makes no sense. You have to group by first and then aggregate, and then you can use the count expression, for instance, in the having clause. And then there's the window clause. If you ever use window function, that happens afterwards. This is here. So some databases support it. Now even MySQL has window functions. They also use the support the window clause like Postgres and Sybase, SQL Anywhere. And now because they're here, you can only use them in select and order by, but not in where as well. Sometimes we would like to use a window function in where. If you ever study window functions, you will run into this, but you can't use it in where, only in select and order by. And this is another thing. In select, we define column aliases. We rename columns. And we would love to use those aliases in where as well, or in group by, because SQL is very verbose. We want to cut down on the syntax, but we can't because they're defined here. Column aliases are defined here, so we can only use them in order by. So this explains a thing or two, right? So if you've ever thought about this, now it makes sense. But that's not what happens. So the interesting thing is, any algorithm that produces the same result as this one is acceptable. And relational algebra is a formal algebra, so we can prove two things to be equivalent. I'm going to give you an example afterwards what that means. And we can see the actual algorithm. There's a way for the database to tell us informatively what the algorithm is. It's called an execution plan. Now, there's an estimated execution plan always, and there's always an actual execution plan. But this one here is from Oracle. Who has seen execution plans? Oh, more hands than I expected, so this is one. That's great. But who has seen execution plans before something goes wrong? While you develop. Excellent. That's how you should do it from time to time. Not only when you have to fix something, but also when you try something. You should try that, because the promise of the fourth generation programming language is still not perfectly kept. Sometimes databases get it wrong, and you should anticipate that. It happens with larger queries from time to time, or maybe you forgot an index, and then just displaying the execution plan will show you that as well. Now, all databases have these. So in Oracle, if you're using SQL Developer, you can just have the explain plan that will give you the estimated execution plan, and next to that button is autotrace will run the query and then give you the actual numbers. That's even more interesting. Postgres has these buttons as well, MySQL as well, SQL Server as well, DB2 as well. They all have this tool. And it's not a formal description of the algorithm. It's an informal one for us to analyze. What happens in this view? I like oracles because it's a tree. All of them are trees, but this one is a tree formatted in a table, so I find it most easy to read and to talk about. But they're all the same kind of thing. So we have an operation on the left side that's like a kind of algorithm that does something which is usually straightforward. So for instance, if you have an index access, which you can see here, So you see here the index axis. That's pretty sure you understand that this is accessing the index in the last name column. And then the interesting columns here in Oracle, it's called cardinality and cost, but it also goes by names like rows. So cardinality is the rows column, the estimated number of rows. This is the most important thing for us to ever analyze SQL, right? So this is where we see what the database thinks it will get out of an operation. Like this index axis will probably give us 6 actors that start with the letter A. That's why the database chose the rest of the algorithm. Because we have 6 actors here, and then we join that with a film actor, and on average, we get probably about 25 films per actor. Actually, it's 27 in this database. And then the combination of that will be 154 rows from this join. So this is an estimate. Right? So the database thinks the join produces 154 rows. So in this case, a hash join was the best choice. Right? So we have to analyze this, because if in fact we're not getting 6 actors here, but 2,000, then something is really wrong. Then the decisions were wrong and the whole algorithm will not be correct. And this is how much time it takes in an encoded format. So in Oracle, it's a weird thing. It encodes the time in terms of disk block I/O time, which is not really a comparable value. And it's also a good reminder that you should never look at the costs, except in some exceptions, which I will explain in the training, but not usually. The costs are treacherous. The costs are used by the database internally, mostly, right? So we should use the cardinality, or the estimate number of rows. And there are some other indicators, of course, in advanced cases. Now, what is the actual algorithm? We read execution plans bottom up. You can imagine the bottommost operation is one that is executed early, and they are coroutines. So they are all run in parallel in some way or another. They don't have to run sequentially. So in this case, this access predicate goes to the index and finds all the last names by letter A and sends each row to the next, pipelines each row to the next operation. So the next operation can already start processing rows when the first one hasn't finished yet. So that's how most databases do it. I don't think the Stream API, the Stream API actually can do that as well with most operations, but if you have a flap map, then it's a hard cut in the current implementation, right? So this is how databases can do it. Now we only have the last name column in the index, so we have to find the first name column as well. And in Oracle, by default, the index is a separate data structure from the table, from the rest of the columns. So we have to do a second access to a second data structure. And the third thing, this is really interesting. Now this is a slight error in this slide. We're not actually fetching it into memory. We were preparing it to put it in the pipeline. We could abort this pipeline early if you have a limit clause. But we're actually loading, if we run the query completely, we're loading all of the film actor relations from the table, from the index in this case. Wow, that's interesting, right? So we get 6 actors only, yet we load all of these 5,500 relationships, even if we only, I mean, in total we have 200 actors, so for most actors we don't need the films, but we only need them for 6. Okay, we'll analyze that later. We'll put both data sets in a hash map. So both data sets are matched in a hash map depending on the join criteria, and then we join them and create another hash map to group rows, or maybe that's the same hash map, but we're using a hashed group by and sort the result. Now, would you have chosen the same algorithm? Who would have chosen exactly this algorithm? Apparently, it seems faster in this case, on this database, on my machine, etc., to load 5,400 rows into memory or put them in that pipeline rather than seeking 6 counts individually. That's what we would have done. We would have looped over these 6 actors. We might have thought, okay, we're going to get maybe 6 actors on average. Maybe you would have thought about that. Maybe you wouldn't. But even if you thought about that, you would have thought, 6 times I will have to go to that other index and count the number of films for each actor individually, and then I'm done. So there are 2 different types of algorithms. Both are correct. Both have their kinds of algorithmic complexity. So depending on how many indexes you have, the first one is always going to be linear. Hash joins are linear. But the other ones are, at worst, I just forgot the word. Polynomial, n squared, or m times n. And in the best case, if you can use indexes, they're a little bit better, but still, I actually don't know which one is better here. If you have 2 times log, I forgot. But this is the kind of question we actually don't want to ask ourselves all the time. Which one is better? Which one is better for us? Which one is better for this case? It depends. Because if you plot these functions, right, if you imagine big O notation were functions, and I've just put that in Microsoft Excel and plotted it, then you have these different curves, and we all know about the curves, and we all know that factorial complexity is one of the worst. We're down here, that's even worse, but you usually never see these in SQL. In SQL, we go until here, the polynomial one. And then, but if you're a developer and you're not taking it seriously, then you work with this kind of data set, and it doesn't matter. That's the worst thing that can happen. It doesn't matter to you on your machine, right? If algorithmic complexity operates on low numbers, then they're all kind of the same. Of course, factorial is very quickly not the same anymore, but then quadratic and linear are almost the same. And actually, quadratic might have some, linear might have some overhead, so you get a better execution plan on your machine. So if you care about this, read the Big O cheat sheet. I really like that. I told you algorithms are boring. They're not boring at all. They're very interesting if you learn about them. So this is a very nice page that explains all the Big O notations, both for CPU complexity, time complexity, which I just discussed, and also for memory complexity, which is usually less important for many things. You mostly care about CPU complexity these days, but both very interesting to learn about it. Well, there's another thing. Another thing you don't think about. Histograms. Now let's imagine we have a bank account table, and we have the amount column. And now imagine we're a retail bank. We're a retail bank, and we have only retail customers. They don't have that much money, so their typical transaction is they go to a restaurant and they pay 50 francs, something like this. So everything is here, close to zero, negative zero, or they are the restaurants, so some restaurants are also with us at the retail bank, and they receive the 50 francs, or here we get the salaries, or here we pay for a new car, something like that, right? So we get a bell curve. This is not evenly distributed. Now, what do you think? Which predicate is better for us here? Or a better question? They're both ranged 4,000, right? There's a range of 4,000 around 0, and there's a range of 4,000 all to the right, between 5 and 9,000. So do both predicates profit from indexing? What do you think? Who thinks yes? Who thinks no? And why? No answers. The answer is no. This predicate here selects maybe 90% of the data. We don't want to use an index. We just go to the table, scan it sequentially, and throw away the 10% that we didn't need. Because we need to select almost all the data anyway. Whereas this predicate might profit from an index. They're entirely different predicates. When did you ever think about this? When you write Java code, about histograms, about your data set. And the database does that almost automatically for you. Sometimes you actually have to just tell the statistics for this column should be a histogram rather than just a distribution metric, which is faster to calculate. Histograms take a little bit more time. But you don't think about this. The database does all the time if you're getting it right. So accessing the index is only worth the pain if it helps reduce the result set. Otherwise, you don't want to use an index. Maybe you will still want to put it there, but let the database decide when to use it and when not. Or maybe you don't even put it there because it's useless. So otherwise, you just read from the table. The database knows all these things. It knows how many rows are returned from a table. It knows how many rows are returned from a query because that propagates through the query. It knows how much cost you have associated when accessing the disk or the cache, or how often is this query run? Do we run it once a day or maybe 1,000 times per second? That changes everything. And the database can adapt on the fly in production. How often is the table accessed? How much memory do we have? How many processes are running parallel right now? Is the operating system doing anything? How does the query perform with this bind variable? Because as you see before, the ranges are different. So if you're using bind variables, it gets a bit harder. Oh, this question. When did you ever ask yourselves, do my algorithms change if I'm using solid-state disk? Of course they do. They're completely different. Because random access is super fast. We don't have to wait for the spinning needle anymore. How many logs do? Everything has a cost in SQL. So how does SQL work? A parsed SQL string produces an expression tree. We have here a plus a minus b. This is an expression tree representation of this query. And then multiple expression trees are equivalent. We can prove that they are equivalent. For instance, this one is the same as this one by the laws of associativity of the plus operation. We can shift the parentheses, and now we get a different expression tree. And we can refactor this once more. And now imagine A is a resource in New York. Suddenly, we have to access it only once instead of twice. Now, that's just a simple example. Behind the scenes, these things are much more complicated and not related to the plus and minus operations. But A can be super expensive, and then we want to have a different execution plan for the same SQL string, right? So each expression tree has a corresponding execution plan and an associated estimated cost, which is being calculated all the time, and the best plan is chosen. So many are evaluated, one is chosen. We can't evaluate all, that's too much time, but the database evaluates quite a few of them. And this is very important. You have never done this. The actual execution cost is compared with the estimate to improve future estimates. Even if the statistics are wrong, some things can be fixed in production, and you have never written Java code that does this. You don't write alternative algorithms, check for some preconditions in production, and then switch them on the fly for arbitrary data sets. Even if your estimates are done, you're not even doing them in production. So there's a special treat here, so Oracle 12 can do this, although most people turn it off. It's still a bit buggy. DB2 can do it as well, and I'm positive other databases will pick up on this feature as well. Adaptive execution plans. While they're executing the SQL statement, they notice, oh, this should be only 6 rows. Now I already got 200. Maybe I should rethink my plan. In the middle of execution, they can fix it. So production is here. Your development environment is here. You're not going to get this right. So you want to use something like SQL, because with SQL, your code stays the same regardless of all of these factors. Now you're going to tune some things in the database. You're going to add some indexes or remove some depending on what you're doing. Maybe you're going to tune some other kind of flag, or you pin some table into memory. That's possible as well, to make sure the table is always in the memory inside of the database. You can do these things, but your business logic doesn't change regardless of the algorithm that you're ultimately choosing. And that's a super cool feature. Think about it. You are more productive. You don't waste time writing that stupid code with hash maps and linked hash maps and loops and whatever and lazy and eager fetching. You write that entire business logic that was obviously better written in SQL. I made the example in SQL, and then the database can evolve your algorithm as it grows or shrinks or whatever happens. So the database is fast as well. Now that you know this, what do you prefer? This or this? Seems obvious now, right? Now, SQL isn't easy. I don't want to say that SQL and tuning SQL is easy. So this is Raphael Winterhalter, the author of ByteBuddy, a famous bytecode manipulation tool for Java. And in his daytime job, he does a lot of Oracle work, and I'm in touch with him. I help him a lot of times. And he's very good at Oracle, actually. But sometimes he runs into these corner cases, and it takes time to learn. But it's very valuable, because we can spend time to fix only really complicated things instead of just extinguishing fires every day, right? So complicated things will always be complicated to fix, and they're more interesting. So I say SQL is the only ever successful mainstream and general purpose fourth-generation programming language, and it is awesome. If you want to see awesome again, watch the other talk where I show much, much more complicated SQL queries than this one. These ones were very simple. So why doesn't anyone else talk about SQL? Why does everyone want to use the latest new tool and do everything themselves? I don't know. I really don't know. But can I write SQL in Java? Yes, finally we can, because we have Juke. I have to do some advertising here. So Juke is type-safe embedded internal diesel that allows you to type check your SQL queries also in Java. That's really great. So when you use Juke, you feel like this as well, or like this. I've seen other evidence from customers, and it's open source as well, from them as well, and this is how we feel. Perfect. Okay, so let's conclude with this talk. Can you do it in the database? Yes. We've seen it's Turing complete. We've seen the Mandelbrot set, although that is a bit extreme, so how to tune that, I don't know exactly, but you can do everything in the database. Can you do it in the database? Yes, of course. Now you know everything, you watch the other talk, then you know even more, and if you want to know even more, just book my training, right? Write down this link, perfect. Can you do it in your database? Now that's a different question. It is usually also yes. Now some databases, I still put MySQL here, they now implemented common table expression for recursion and window functions, so they're catching up. I will soon have to revise this slide, but they still don't have any hash joins, so they only have nested loop joins. So they're actually implementing every query as you would have done manually in the client, still. But they're improving. They are now, with MySQL 8, added a better cost model, so it gets better and better. You have also Postgres, which is quite good, but the commercial ones, they're really amazing. The kind of queries they can tune, amazing. I consult with a large Swiss bank, and they run queries of maybe 500 lines of execution plan on a billion wrong-throw tables, join that billion wrong-throw tables several times, and runs in a couple of microseconds. right? So we run these things with cumulative sums and stuff like that. Should you do it in the database? Now this is always the question, right? There's always that consultant that says, no, business logic in the database is horrible. No, you don't do that. But I'm just kidding. You should, because we've seen the reasons. Don't listen to these people, right? So I don't talk about store procedures here. I talk about SQL, which is a language for set-based thinking. And it's because of this that it's so good. We're thinking in terms of data sets, how we should do it. And we're not iterating over individual rows, because that is not only boring, but also slow. Do long list titles attract attention? Yes, you're at a Java conference and everyone skipped lunch and they came to this talk, so this has worked as well. We can confirm this as well. Will this talk ever end? Yes, on time. Google 10 SQL tricks to find the other talk. You can also read the transcript. Thank you very much. These are my coordinates.